Okay, welcome to the third of our 5-part series on modular arithmetic. In this section, in this YouTube, we're going to look at division and linear congruence. If I can work my screen, here we go. Division and linear congruence. Okay, so you'll recall that we've picked up a fair bit already, and we're understanding modular arithmetic hopefully a little bit better. And we've got addition and subtraction and some multiplication rules and some power rules. Really important, that power rule. We'll come back to that when we look at Fermat's little theorem. That was that if A is congruent to B in some mod, then A to the n is congruent to B to the n, and if we get b to be equal to 1, isn't this a powerful thing? So we've got all that, and we've picked up some things. We haven't really looked at division, and this is where we'll go in this YouTube. So what we need to know here for this piece of work is that, importantly, look, if A is again a starting point equal to B in mod m, all right, then now what we're going to do is we're going to in order to do some solving of some linear congruence equations, we're going to need to divide. All right, so this is important. We can divide through by a d, integer d, but what that will do, it'll change our modulo value. And our modulo value, if we're dividing through by d, is changed to whatever it was, m, divided by the GCD, the greatest common divisor of d and m. All right, now that might, if d and m are a coprime, then that's just 1, so that doesn't change our modulo value. But if it's not 1, then obviously that's going to divide by whatever it is. So we can use this to solve linear congruences. We can use this to solve linear congruences. That's what they're called, right? So that's the language. So let's have a look at an example. E.g., different color. Let's go to black. E.g., solve. How's it written? How does it look? Solve, or find the values of x, or solve for x. Given, let's say solve for x given that in the first example, 2x is congruent to 7 in mod 5. Right, so let's have a look here. Firstly, this 7, I want to divide by 2, but I can't have fractions, right? So this 7 is going to have to change. And you know, I can just 2x, if 7 in mod 5 is just the same, I can add 5 to it and get 12. It's still the same, isn't it? 12 in mod 5 is the same as 7 in mod 5. It's just got a remainder of 2. And remember, in modular arithmetic, the remainder is it. It's the point. And if that's the same, then our values, then our statements are the same. So 7 in mod 5 is the same as 12 in mod 5. So I can just rewrite that. Isn't that beautiful? To 2x is congruent to 12 in mod 5. Now I'm going to divide through by 2. So x is congruent to 6 then. Now I'm going to say it's the mod is now 5. So I've divided, d is my 2. Now my GCD of 2 and 5 is 1. So my mod doesn't change. It's 6 in mod 5. But hang on, so I've got to simplify that. 6 in mod 5, we always write that the smallest number, and that is 1 in mod 5. So x is equal to, or congruent to, 1 in mod 5. I've solved a linear congruence equation. Isn't that exciting? Let's have a look at second example. Again, we're solving for x given, in this case, 6x plus 5 is equal to 8. And that's in mod 9. All right, the first thing we're going to do is we're going to subtract that 5. Always use these congruence statement. So subtract the 5, so 6x is equal to 3 in mod 9. Is that okay? We've just subtracted 5 from both sides. We know that that's okay. We can do that. So 6x is equivalent of 3 in mod 9. But I now want to divide by 6, and that will give me a half here, so that's no good. So I'm going to add 9 to this. Is that going to work? Add 9 to this. 12 in mod 9 is the same as 3 in mod 9, but that's got the added benefit of being divisible by 6. So therefore, x is equal to dividing by 6. Remember, d is 6, but 6, 9 have a GCD of 3. So I'm now going to have to change my mod to 9 divided by my GCD of 6 and 9, which is 3. So I'm 9 divided by 3 is 3. So I'm 2 in mod 3. All right, now just make a little side note there. That 3 came from 9 divided by the GCD of 6 and 9. 6 being this number here that I divided by, that's my D. All right, and that's equal to my GCD of 6 and 9 is 3, which equals 3. That's how we get the 3 there. All right, let's do another example. This is too much fun. 11x is congruent to 5 in mod 8. All right, if you think you're good at this, pause now. Pause and come back. Okay, you're back. Right, I'm not going to divide by 11. We're not doing that. In mod 8, this is also equal to 13. It's also equal to 21. I'm going to keep going until I've got a multiple of 11, aren't I? So I might even have to write some of this stuff down. So 5 in mod 8 is the same as 13, but I'm still dividing by 11. That's no good. It's the same as 21. Divided by 11 is no good. I'm still adding 8. 29 divided by 11. 37 divided by 11. 45 divided by 11. I'm still not there. I'm going to keep adding 8 to 53 to 61 to 69. Keep adding 8 to 77. I'm there now. I'm 77. So 11x is congruent to 77 in mod 8. Now just check here, just stop and check. In mod 8, that's 5 because 9 8s are 72. All right, same thing, but now I can just divide by 11. So I get 7 in what mod though? Now what have I divided by? I divided by 11. So that's my D, and the GCD of 11 and 8, well that's 1. So my mod doesn't change. So x is equal to 7 in mod 8. Okay, one more. And that will be 25x equals 10. 25x is congruent to 10 in modulo 30. All right, so go away and pause the video now and go and solve that. Okay, in mod 30, I'm not going to divide by 25 here, but I can. All right, let's work this out. I'm going to add 30. I'm going to add 30. I'm going to add 30 until I get a multiple of 25. I've got it. So 25x is congruent to 100 in mod 30. That's this first step. Now I divide by 25, but my mod is now 30 divided by the GCD of 25 and 30. The GCD of 25 and 30, so it's 30 over the GCD of 25 and 30. The GCD of 25 and 30, this here, that value there is equal to 5. So it's 30 divided by 5 is 6. So I've got 4 in mod 6. And that's my solution. X equals 4 in mod 6. Put that in there. 100 is equal to 10 mod 30. Absolutely right. Okay. Now, one more example. Okay, the last example is just one to highlight that actually there can be, like with any equation, there can be no solution. So when 3x is equivalent to 5, it's supposed to be a 5 there, apologies, 5 in mod 12, and we're looking for 17, and we're adding, and we're adding, and we're adding, and we're looking for a multiple here of 3. But what we're finding is that, well, we're not getting there. And why aren't we getting there? We started because what we're doing is we're adding 12 each time as a multiple of 3, and we started with 5. Now we're trying to get 5, we're trying to get 12a plus 5. We're trying to get this to be a multiple of 3. And we're just not going to get there because, look, just divide by 3 here. We're not going to get b so that we've got an integer. So in this case, there is no solution. Remember, we're looking for an integer. We're looking at this is discrete mathematics. So no solution there. Okay, time to go and have some fun with exercise 5C, and I feel like I've done enough examples there for you to be able to do exercise 5C, and then we'll come back and look at 5D. See you later.